Hello, AP Stats. I am hoping you are putting away your cell phones and getting out your notes because we have a lot of things to get through today. So first, just some reminders about the sampling distribution. We talked about the sampling distribution of proportions, p-hat, and we can summarize the facts about a sampling distribution of p-hat is as follows. Now keep in mind a sampling distribution can be about a proportion, a sample proportion. It can be about a sample mean. It can be take a sample and find all the maximums of all these different samples. The trick is the sample size, n, has to always be the same. So if, for instance, you're taking a sample of 10 and you find the maximum of 10 and then you take another 10 and you find that maximum and you sample again and find that maximum. You do all possible samples of size 10, finding the sample maximum, the sample proportion, the sample mean, the sample IQR. All of these are sampling distributions. In AP Stats, the sampling distribution for proportions and the sampling distribution for means are the two that we really concentrate on. So we talked about for sample proportion, if we choose a simple random sample of size n from a population of size n, with proportion p of successes, and p hat is that proportion of successes just for the sample. The mean of the sampling distribution is going to end up being the true p, and the standard deviation will be the square root of p times q over n. There it is right there. So as long as you can use that standard deviation formula as long as you have the 10% condition satisfied. So remember, this 10% condition goes with standard deviation. So as long as 10 times the sample size is less than the population, because we talked about you want a really large population in relation to the sample size, because then it's really not the fact that you might be sampling without replacement isn't so significant, because you're taking out such a small sample. That proportion is very small, so independence isn't as big of a deal. As n increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, you have to check the normal condition. So our first condition was the 10% condition. That's for standard deviation. And the second one is the normal condition, where NP and NQ both have to be greater than 10 in order to use norm CDF and norm PDF. When we choose a simple random sample from any population, the sampling distribution of the sample mean is centered at the population mu and is less spread out than the population distribution. So here's what our picture would look like. We have described the mean and standard deviation of the sampling distribution of sample mean x bar, but not its shape. So what's happening? We know it's going to be approximately normal, but in one important case, there's a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution. If the population distribution is normal, then so is the sampling distribution. There is no matter. It doesn't matter what your sample size is if your population was normal. But suppose it's not normal. Then you have to check another condition. So here's an example. The height of young women follows a normal distribution. I always underline that as I go, with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5. So this is just a normal CDF problem, like we've done before. The height of the woman is normally distributed. Remember our normal notation. And we can get our z-score and draw our picture. We don't have to get our z-score necessarily, but make sure you know that relationship. And we just find this probability by doing norm CDF of 66.5 to infinity, comma, the mean of 64.5, comma, the standard deviation of 2.5. The probability of choosing a young woman at random whose height exceeds 66.5 is about 0.21. So now this is a whole different question. For a sampling distribution question, they'll ask you for the probability that a mean or a proportion is greater than or less than something, and they'll give you an N, they'll give you a sample size. So that's always a big clue that you're going to still do norm CDF, but you're going to have to find a different standard deviation. So our mean of our sampling distribution here, mu, is equal to the true mu, 64.5, but that we've got to calculate a new standard deviation. This is what makes this problem different. 2.5, the original sigma, divided by the square root of n, which is 10. And that gives us a standard deviation of 0.79. So it is following a normal distribution. We know that because the original population was normal. We can find a z-score if we wish. We can draw it if we wish. And the probability comes out to be 0.0057, a good bit smaller. It is very unlikely, less than 1% chance, that we choose a simple random sample of 10 young women whose average height exceeds 66.5 inches. So we can see the difference in the probability. So to calculate this one, we do exactly the same thing on our calculator, norm CDF of 66.5, comma, infinity, comma, the mean of 64.5, comma, but a different standard deviation. We'll put in here this standard deviation of the sampling distribution is 0.79. So that's really the main difference in calculating those two problems. And there's the picture, and you can see how much less variable the sampling distribution is to the population distribution. And see right here, that same 66.5, how less likely it is to fall in that area if you're talking about the mean of a sample of 10 women versus if you just talk about one single woman out of the whole population, because you will have taller people. So, very important theorem, central limit theorem. Most population distributions are not normal. So what do we do when they're not normal? What is the shape of the sampling distribution of sample means when the population distribution isn't normal? It's a remarkable fact that as the sample size increases, the distribution of the sample means, all the x bars, changes its shape. It looks less like the population and more like the normal distribution. So this is what we did with our pennies, our ages of the pennies. It was definitely skewed to the right when we found the ages of 1 penny, but then the larger our samples became, the standard deviation decreased and the shape should have become more normal. When the sample is large enough, the distribution of sample means is very close to normal, no matter what the shape of the population is. How large is large? Well, that depends on the shape. So if we draw a simple random sample of size n from any population with mean mu and a finite standard deviation of sigma, the central limit theorem says that when n is large, the sample distribution of the sample mean is approximately normal. We can abbreviate the central limit theorem as CLT, and you can always use that. So here's some different distributions. It's actually the same population here. Consider a strange population distribution from Rice University. Sampling app on, you can find that on the web. And notice how here n is 2. These are sample means of here a sample size of 5. Here your sample size is 10. And here your sample size is 25. So even though the original shape is crazy, the larger the sample gets, the more that distribution of sample means gets to normal. So how large should large be? Well, we're going to let n be larger than 30. That's a good number to use regardless of the shape. Now sometimes it doesn't have to be as large if it's a fairly symmetric distribution starting out versus if it's a really skewed one or one with a lot of outliers. But n is greater than 30 is a good guideline where your shape will end up being approximately normal of your sample means. So here again is 4 different shapes. Here it's clearly skewed right. This could be similar to our penny problem. Here n is 2. So all these are sample means of, from a sample of size 2, size n, and size 25. And again, you can see how it gets closer to normal shape. So here, problem, based on service records from the past year, the time and hours that a technician requires to complete preventative maintenance on an air conditioner follows the distribution that is strongly right skewed, and whose most likely outcomes are close to 0, and the mean time is 1 hour, and the standard deviation is also 1. Your company will service a simple random sample, so there's your N. That's your clue to use a norm CDF problem using X bars. 70 air conditioners, you have budgeted 1.1 hours per unit. Will this be enough? Since the 10% condition is met, so always show that with numbers. 10 times 70 is 700 air conditioners in this population, so we're going to just assume that there's a large enough population, more than 700 air conditioners. The sampling distribution of the mean time spent working on the 70 unit has a mean of mu, which is 1, and our standard deviation, since we have more than 700 air conditioners, we can use that standard deviation formula. 1 over square root of 70, you can get 0.12. The sampling distribution of the mean time spent working is approximately normal, since our N is greater than 30. Our N is 70, so that's the rule of thumb that allows us to use our normal distribution. There's our picture. Always good to draw your picture. Shade the area you need to. We need to find what's the probability that the mean is greater than 1.1. So we're going to put in our calculator, norm CDF of 1.1 to infinity, comma, the mean is 1, and the standard deviation is not 1, but it is 0.12, so make sure you make that change since it's a sampling distribution. Remember, you want the probability that the sample mean is greater than 1.1, which comes out to be about 20%. If you budget 1.1 hours per unit, there is a 20% chance that the technicians will not complete the work within the budgeted time. And that's a fairly large number, 20%.